Hi, this is Nick Fryer, and today I'm talking about Lab 1, which has to do with constant velocity motion. Before I get started, a quick introduction. There are some key physics concepts that are the basis of this lab. So, first is the idea of constant velocity, which occurs when the net force acting on an object is zero. So, in other words, there's no net force, so the position change over time stays constant. This is according to Newton's first law, which says that an object moving at constant speed in a straight line will continue to do so until a force acts on it. I'll also consider the position and velocity update formulas, which are shown here. Note that the net force is zero, so final velocity is equal to initial velocity, which in turn is equal to the average velocity. This is what I do see in the lab with some error, but that will be shown shortly. So the main purpose of this lab is to model the motion of an object, which in this case is a battery, when it's moving at constant velocity. I aim to compare that observational data that I gained from the tracker software with predicted data that I gained from GlowScript coding. I'll use the ideas from the previous slide along with Newton's second law to create the model. Note that Newton's second law states that the time derivative of momentum, or the mass times the time derivative of velocity, is equal to the net force. Since mass is non-zero, the time derivative of velocity must be zero for the net force to be zero, so the velocity cannot change over time. I do have to make some assumptions. One, I have to assume that air resistance and friction are negligible. And two, I have to assume that the battery only moves in the x direction. So left and right, not up and down, not forward and backward. As a quick note, the system that I'm considering is the object that I'm studying. So in this case, the battery, and the surroundings are everything else. So the table that it was on, the earth, etc. So this is the tracker analysis of my moving battery. It is admittedly a little blurry, but you can see that the red dots are there tracking its position over time. The battery moves from left to right, so the x-axis was chosen to be in the positive direction, and the origin of our coordinate system is the center of the screen, meaning that the position moves from negative to positive. But because we're measuring relative positions rather than one specific one, it really doesn't affect our analysis at all. So this is the important data for our tracker observations. So the mass was about 23 kilograms for the battery, 23 grams, or 0.023 kilograms. The initial time of tracking started at 1.867 seconds. This was actually a conscious choice because before then I was actually pushing the battery, which is an external net force that would cause the velocity to change over time. The final time of tracking was 2.933 seconds. The initial position was to the left of the center, meaning that it was at minus 0.118 meters. And the initial velocity, which I got just from calculating the first two data points, the average velocity between those, was 0.2227 meters per second. And it's positive, which is what we expect since it's moving to the right. This is the important GlowScript code that I used for the computational model. It takes into account our initial position and velocity vectors from the previous slide, as well as the position and velocity update formulas that I mentioned earlier. Note that the position that I list here, the initial position, is a little bit different. That's just because in order to line up the two times, I had to go one step before the observation time started, just to make sure that they started at the same time. This is how we create an iterative model. So these are the results from GlowScript. As you can see, the position is increasing at a constant rate, meaning that the velocity is constant, which is exactly what we would expect. Here's the graphical comparison between observed and predicted positions. As you can see, they're pretty close. There is a little bit of deviation, mostly towards the end as time moves on, which is due to some error that we kind of expect. I found that the observed positions and velocities were similar to the predicted ones that the GlowScript code generated. They tended to get a little less accurate over time, like I said, so that suggests that there's some other external forces that we assume to be negligible that are actually acting on the battery. So some possible sources of error include not accounting for those external forces, as well as rounding during calculations, and placing tracker data points slightly off from where they should actually be. When I was doing my observational data. So what if I had chosen to use the minus x direction rather than the positive x direction for my axis? Well, positions would go from positive to negative or negative to positive because they would be flipped along the x-axis. Velocity would change to be negative rather than positive. It would be basically an exact mirror of what we saw. but the speed would not change because speed is just the magnitude of the velocity. And can we say how many external forces are acting on the battery? Not really. Certain forces are known, like gravity, and we know that there's some sort of air resistance and friction. But for example, there's particles on the table that are impossible to account for, and other gravitational forces from other objects around the battery. So they're impossible to know. Thank you, and I hope you enjoyed.